Hello, everyone, and welcome to the Foundational Statistics for Forensic Toxicology webinar series. Today is session 3, Statistical Tests and Hypothesis Testing. We are excited to welcome guest presenter Dr. Rajit Dihane, chemist and scientific coordinator in the Department of Toxicology and adjunct professor in the Department of Environmental and Occupational Health with the University of Montreal School of Public Health. Without further delay, I will turn things over to Dr. Dihane.
All right. So hello everyone. I'm really thrilled that I get to contribute to this series today by discussing hypothesis tests with you. So a bit of background before we start. So a large chunk of my PhD in chemistry dealt with the development of statistical methods applied to forensic toxicology. And that's kind of when I saw that there was a real need in the forensic toxicology community to learn more about this topic and to have some reference that started at a real introductory level for forensic toxicologists and not introductory level for, bachelor math students. To clarify what the best practices were. So I started publishing the statistics series in the TF Bulletin in 2019. So Sue referenced that last webinar a week ago. So unfortunately, this has taken a bit of a backseat as I've had 2-year-long parental leaves in the past years. But I still there are still 8 chapters of this series that are published so far. So I really am a chemist by formation. I have very little formal training in statistics, and I want to highlight that the thing about learning statistics is being confused is normal. It just means that you're learning, and as Sue and Arya pointed out, you're moving to the stage where now you know that you don't know something, and it's normal to be confused when you're dealing with a topic that is not your specialty. Of course, and I mean, believe me, when I got to explaining internal standards to a friend of mine who has a PhD in statistics, well, let's just say it took us a bit of time before he finally understood the gist of it. And so really the best advice I have for you is to come back again and again and again to these topics that are hard or confusing. And one day, I swear, things will just fall into place. And so repeated exposure is really key to understand all of this. And that's why I had my little one listening to Sue's webinar last week. So I'm joking, of course, but you do what you can when the babysitter is sick. But the message still stands. Repeated exposure is really key to integrate all of these concepts. And you will see it's just the best feeling when everything finally falls into place. So having said all of that, let's jump into hypothesis tests. Now, despite what the title of this webinar might suggest, I want to clarify that statistical tests and hypothesis testing and null hypothesis significance testing, they're all equivalent terms. And while some of you might know what I am referring to by hypothesis tests, it might be unclear for some others. So here are some of the most common hypothesis tests that you might have run across. So if you don't know exactly what they do, their name might still ring a bell at least. So you have, for example, the F-test, the T-test, the analysis of variance or ANOVA, and you have Grubbs test. So these tests and other like it is what we want to discuss today. And I know that right now, for most of you, these are kind of black boxes, probably, right? So you have data and you put it inside a hypothesis test, and then abracadabra, you get a result, a p-value, which how exactly are you supposed to interpret it? What does it mean? What does statistically significant mean? Is lower than 0.05 significant, or is it the opposite? So no worries, we'll try and make some sense out of all of this today. So first of all, I want you to understand that under the hood of all hypothesis tests is the same engine. Now, you might think that you need to understand every one of them separately. And really, how could you do that? Because there are so many of them, the list is so long. But no, if you understand the general framework, you pretty much understand them all, actually. And here I could start with an example and take you through the whole process with numbers, but I find that this might be detrimental to our goal of understanding the general framework. So if the only thing you get out of this webinar or this slide and the next, you will already have gained a lot. So what's the general framework of a hypothesis test then, told in a numbers-free way? So first, you assume that there is no difference between the groups you want to test, no difference in whatever you are testing for. For example, no difference in variances or no difference in means or no outliers present. So this is your null hypothesis, H0 or H0. Second, okay, well, if there is indeed no difference between the groups, what do I expect to see in my data? Third, what do I actually see in my data? Fourth, what is the probability of obtaining this configuration, of observing this data, if my null hypothesis is true, and there is indeed no difference between the groups? Well, that is the result of a test. That's the p-value, this probability. And finally, if the probability is too crazy bananas improbable, then you say, okay, I reject the null hypothesis of no difference because it's really too improbable that it's true. And I accept that there is indeed a difference between the groups. So you accept the alternative hypothesis, H1, and that's when we say that there is a statistically significant difference. So that's it. That's how all hypothesis tests work. So before we get into numbers, I want to cover an important and critical even concept while all of you are still awake, or I'm hoping at least, the interpretation of the test result. So what does a p-value mean? The p-value is the probability of obtaining this result, or a more extreme one, assuming that the null hypothesis is true, meaning assuming that you have no difference. So this is super important, and that's why I put it in a big red frame. So it's not the probability that the null hypothesis is true given the data. It's not the chance of successful replication of your experiment. And it's not the probability that the results were obtained by chance. And I'm insisting on the correct interpretation here because it's such an easy mistake to make. The language slip, it really comes easily, and you can get slammed hard by reviewers or in court or during your PhD defense, true story, for this kind of thing. But if you are careful, it's also easy to avoid. And for now, the distinction between the correct interpretation and the incorrect one, it's probably quite a fuzzy one, to be honest, and that's fine. As I've said before, give it time. At least now you can come back to this slide when you want to write down the correct conclusion. Okay, so you do get this p-value, the probability of obtaining this result or a more extreme one, assuming that the null hypothesis is true. But what do you do with it? Well, we've touched up on this already, but if you have a p-value below 0.05, you go, oh, geez, it seems rather unlikely that I would obtain this kind of result, right? It's less than a 5% probability. So the null hypothesis, it's probably not true. So I will accept the alternative hypothesis, that is, that there is a significant difference between the groups. And if you have a p-value above 0.05, you go, sure, okay, I guess it's possible to obtain these measurements, even if there's no difference between the groups. So I will accept the null hypothesis, and I will conclude that, the groups are the same, or there is no outlier, or whatever the case may be. So of course here I've used a 0.05 or 5% threshold just because it's really common in science, but that can vary depending on what you want. Okay, so now is the time to introduce some actual numbers and maths into it. So let's start with a simple example. So let's say I am comparing two methods that perform quantification of ethanol in blood. So method A is our lab's method historically used to perform this task. But recently we've developed a new method, B. And we want to compare both methods to make sure that they give the same results within their margin of errors anyways. So how do we do that? And how do we assign a probability to the result? So to help us answer this question, we've analyzed 6 QC samples of a target concentration of 100 milligram percent under both methods. So it might seem incredibly complex at first. So how can I even calculate a probability? Am I a fortune teller or what? But actually, it's easy enough if we rely on what we've learned last week, distributions. So let's say that you know that ethanol measurements on a quality control sample, they take up a normal distribution with an average of 100 milligram percent and a standard deviation of 3 milligram percent, just like this. So remember that the standard deviation, right, it describes the spread or the width of the distribution. Okay, so what is the probability here of obtaining a quality control measurement of 105 milligram percent or more? Well, you know that the area under the whole normal curve is 1 or 100%, right? Like it would be for any other probability density function. So any probability density graph like that, the area under the curve is 1. Okay, so the probability of a measurement falling between 105 and infinity is the area under the curve. And here, this area under the curve, it represents 4.78% of the whole. So this would be a p-value of 0.0478. And of course, the exact value of the area under the curve, you obtain that using Excel or any other statistical analysis software. Okay, so sure, you might say, but that's with the data distributions. It's not for a hypothesis test. And with hypothesis tests, we'll be handling, well, I was going to say apples and oranges, but it's actually even more diverse than that. We'll be testing for different variances, different means, and the presence of outliers. And even if we limit ourselves to, let's say, the means, you can have various sizes of difference between the means. So you can have small or large differences between the means, and you can have small or large variances, just as there are hundreds of different and delicious cheeses. So that's my French side speaking. So we really do need a common language to properly compare all of these different items. So what we'll do is, instead of looking at the distribution of data, like we've just done with the ethanol measurements, we would look at the distribution of test statistics. So what is a test statistic? Well, it's just a computed value representing what I want to test. So it's a single number that summarizes what I'm after. So for example, in the case of our method comparison, we really want to see if there is a difference between both methods. So how do I summarize the difference into just one number? Well, something that's highly generalizable is a normalized difference. So a normalized difference or a relative difference. So the T statistic that you see here is calculated by taking the difference between the averages of both groups and dividing by the pooled standard deviation for the two groups. So remember the X with a little line on top, it's called X bar, and it represents the average for a group. So, okay, well, if I calculate the t-value for these two methods, I obtain t equals to 2.6. So what's next? Well, in a very useful turn of events for us, these test statistics, they have a distribution too. Cool, no? So to be precise, we have knowledge of how this statistic t would be distributed under a simple defined situation known as the null hypothesis, or H0. So typically, as we've seen, the null hypothesis is the hypothesis of no difference. because it's more simple, it's more generalizable. So, there's only one way that two groups can be the same, right? Their difference is zero, but there are plenty of ways that they can be different. They can be different by 1, 2, or 2,000 units. So in our example with the ethanol quantification methods, the null hypothesis H0 would be that the measurements average for method A are the same as the measurements average for method B. So we can also define an alternative hypothesis, H1, where there is a difference in the measurements average. So this is how the t-statistic is distributed under the null hypothesis, H0. So it looks remarkably like the normal distribution, right? But it's a bit different, actually. The extreme values have higher density, higher probability, or in the stats lingo, the tails of the distribution are fatter. So like any distribution, test statistics distributions, they're fully defined by their type and by distribution-specific parameters. So typically one of these parameters, and sometimes the only one, will be degrees of freedom. So we've discussed this in the first session of this webinar. Remember, degrees of freedom. So degrees of freedom for this statistic, they're the total number of measurements minus 2. And just like changing the mean and the standard deviation will have an impact on the shape of the normal curve, well, so will changing the degrees of freedom will have an impact on the t-distribution shape. So that's what we see in this graph. The tails of the distribution, they get fatter when the degrees of freedom decrease. So this is actually some food for thought. And I'm not going to go in detail into that, but I want you to keep that in mind and maybe reflect on this after the webinar. This right here is the key to why making more measurements is important for efficiently detecting differences between groups. Okay, well, now that we have the test statistics distribution at hand, it's actually child's play to associate a probability with this result we obtained from the measurement values. So remember, the value we calculated for the t-statistic using our data was 2.6. Well, what is the probability that we would obtain a t-value of 2.6 or higher if the null hypothesis is true and we have no difference between the groups, and this is the distribution of the t-statistic? Well, we get the area under the curve with the help of a software, of course, and it's 1.35% or p equals to 0.0135. Easy peasy, it's not more complex than this. Okay, so it's not complex, but obviously I've skipped over the part where you need to build and choose these test statistics that adequately represents what you want to test and figure out what their distribution are. Well, fortunately for us as forensic toxicologists, we can just leave that to hardworking mathematicians. They've already developed quite a bit of these test statistics for the most common situations, and that's what all of these different hypothesis tests are. So we can just focus on using what has so kindly been built for us. So we'll come back later to what the different tests are and in what context they are used. So another way to summarize hypothesis tests is this. So the data we examine, it's on trial. It's innocent until proven otherwise. So in other words, the null hypothesis of no difference, it's true until I can prove otherwise. Well, assuming innocence, assuming that there is no difference and H0 is true, how likely is it that I would obtain the data that I have in front of me? How likely is it that we'd have all the pieces of evidence presented by the prosecutor if the accused was really innocent? Well, we typically set that threshold at 5% or 0.05 in scientific publications, as we've said before. So I hope that this makes you realize something. Hypothesis tests, as we typically use them with a low p-value threshold, they're heavily biased towards the null hypothesis. So your data set is considered as stemming from a no difference data set until proven otherwise. This is a conservative approach, right? If we are to claim a change from the status quo, for example, saying that a drug works, we better be certain of our call. So it's super logical that it would be said this way, but it's also extremely important to keep in mind. Too often I hear people go, well, the means are different, but it doesn't come up as a significant. That's weird. Well, no, it's not. It just means that the difference isn't big enough that the test considers it's beyond the shadow of a doubt. But this type of setting with a heavy bias towards the null hypothesis, it's not always appropriate. So for example, in our ethanol quantification method comparison example, erring on the side of caution, it means investigating any potential difference, not favoring the null hypothesis of no difference and assume that there is no difference until proven otherwise. So, of course, if we want to, we can tip the scales, right, towards the alternative hypothesis by increasing the threshold or the alpha level. To which level exactly, the decision is yours. But I just want to make you realize that an alpha level of 0.05, it's not always your best choice, and you can have really good reasons to change it. So that's it. All of this means that there is actually a 5% chance that we have rejected the null hypothesis when in fact it's true. We'll say that there is a difference when in fact there isn't. So we call this the type 1 error rate, and it's also labeled alpha. Of course, if there is a type 1 error, nobody here will be surprised to find out that type 2 error exists as well. So type 2 is a false negative when you don't believe something is happening, but it is. So let's go over this again with a visual representation. So let's say you are doing a t-test and your null hypothesis of no difference is true. So this is how the test statistic is distributed. My decision threshold is here, so anything above this line, I'm calling a significant difference. Well, even if the null hypothesis is true, sometimes, it's unlikely, but sometimes the test statistic will come up on the other side of this threshold. And that's my type 1 error rate or false positive. I will be calling a difference when in fact there is none. Now, let's say that my alternative hypothesis is true, and there is indeed a difference between the two groups, a real difference. So if I were to redo over and over and over again my measurements in my hypothesis test, this is the distribution that I would obtain for the calculated t-statistics. But my threshold for calling something significant, it remains the same, right? Because I'm still in the mindset that my null hypothesis is true. So anytime, just by chance, the t-statistic, it falls below this threshold, well, I'm incorrectly saying that there is no difference, or I'm committing a type 2 error. So by the way, if at this point you're getting a bit confused, it's fine, don't worry. It's not an obvious thing to understand the first time around. So you can come back to this and mull this over in your head after the webinar. So I've said that the type 1 error rate, it's alpha. So it's the threshold that we set for the test. Typically, it's 5%. But how do we calculate the false negative rate or the type 2 error rate? Well, unfortunately, things get a bit more complicated. So the value of beta, it depends on several characteristics of the true underlying data. But you don't know exactly what the underlying data is. That's why you're doing a test. Okay, so see what the issue is here? Generally speaking, if you want to decrease the type 2 error rate, you want to have large differences between the groups. You want to have really precise data, a high alpha value, and a large sample size. So basically, the more the distributions are clearly distinct from one another, the less false negative issues you're going to have, which I realize is like, duh. The more they're distinct, the more you can say they're distinct. Well, yes. I mean, what you want, it's not magic. So if we come at this whole thing from a glass half full perspective instead of looking at our error rates, we could also ask the question, what is our ability to detect a true difference between the groups? And that's the power of a test. So the calculation is quite simple. It's 1 minus beta. So it's quite simple, but of course it depends on exactly the same parameters as beta, doesn't it? The power will be increased with large effects, small spread, high alpha, and large sample sizes. So I've very rarely seen type 2 error or power discussed in toxicology papers where hypothesis tests were performed. But this is actually a big part of evaluating the performance of a statistical test that we have just used. So it's super relevant and it shouldn't be overlooked. If beta comes out at 80%, I mean, there's a big fat chance that we're missing something and we should make changes to the experimental setup. Okay, so here's one topic I've avoided touching up to this point, the one tail, two tails, or one-sided, two-sided distinction. So you might have heard of this because, well, software will require you to specify whether you want to carry out a one-sided or a two-sided test when you ask for the computation of a p-value under any test. Or if the software doesn't ask for it, just means that by default, they're choosing one or the other. And second, this characterization, it will, or at least it should, appear in the description of the test carried out. So for example, if you might read a one-sided t-test for groups of unequal variance. Okay, so what does this refer to anyways? Well, essentially, it's linked to whether you are looking at an increase, a decrease, or simply a change, either increase or decrease, as a significant result. So for example, if I am testing the stability of a compound in solution by comparing quantification results at week 1 and week 4, then I am looking for a decrease in concentration, right? It's a stability study. If there is instability, it should decrease. So here I should use a one-tail test. If, another example, I am looking at whether neoformation of GHB occurs in a sample by comparing concentrations at time 0 and 2 months later, well, then I'm only interested in whether there is an increase, right? So I'm looking for neoformation, the creation of the molecule. Well, again, I would use a one-tail test. If we come back to our method comparison example, where we compare methods A and B for the quantification of ethanol, then we're just looking at whether these two methods are different. We have no reason to believe that B would yield higher results than A. Well, in this case, we would use a two-tails test. And here I want to insist on the fact that this is an a priori decision. I need to take this decision based purely on the hypotheses I am examining, not based on any of the data I've collected. So this decision is taken before I have even collected a single measurement, or at the very least without looking at them. So I shouldn't go, oh, look at that, method B seems to be giving higher results. I'm just going to check if those results are higher than method A and use a one-tail test. No. If you have no fundamental reason to look specifically for an increase or a decrease, then you stick with two tails. Okay, well, what difference does this make in carrying out the tests? Up to this point, all that I've shown you was actually one-sided testing. So does that mean we should throw all of this procedure in the garbage if we want to do two-sided testing? Well, of course not. Actually, almost everything still holds. So we still compute a test statistic representing whatever we are looking for. We still compare this computed value to a known distribution of the statistic under a null hypothesis of no difference. We still obtain a probability of obtaining this value, or a more extreme one, assuming that the null hypothesis is true. But this time, instead of looking at the area under the curve for one side only, we look for the area under the curve on both sides. So under a one-tail test, we go, okay, I've calculated my t-statistic is 2.6. What's the area under the curve of the t-statistic for values of 2.6 or more? and we get 1.35%. Under a two-tails test, we go, what's the area under the curve for values higher than 2.6 and for values lower than minus 2.6? Because we recognize that a value lower than minus 2.6, it would be just as extreme as a value above 2.6. The only difference is that it would be a negative difference instead of a positive one. And now the area under the curve, it has doubled to 2.70%. So this does have an impact on the type 2 error rate of a test and thus on its power. One-tailed tests, they're more powerful than two-tails tests, as you might have deduced just by the fact that the p-value doubled in the two-tails case. So to simplify, you might say that by looking for a change in either direction, you are spreading your attention a bit thinner and your reaction time will be longer than if you were focusing all of your attention on looking at a change in a specific direction. But again, choosing to use a one-tail versus two-tails test, it's an a priori decision based on the system you're examining. So unfortunately, you can't just choose a one-sided version of the test just because it's more powerful. Okay, well, now that we know about the inner workings of a hypothesis test, shall we go and apply some? What are these hypothesis tests? Is there a list? Well, here's a partial list. There are a lot of hypothesis tests available, a lot. So how do we deal with this? Do we need to know all of them? I mean, well, truth to be told, some are more useful than others, and they will come up time and again in textbooks and data analysis. So let's round up the usual suspects and look at some of the basic parametric tests. So the first tests on our list have somewhat complicated names, Kolmogorov-Smirnov and Kramer-von Mises. So these two, they test for the fit between an experimental and a theoretical distribution. So for example, you can use them to test whether your data is normal, comparing your data's distribution to a theoretical normal distribution. So remember, last webinar, Sue introduced you to some tools to check whether your data was normal, or rather some tools to look at whether your data was not normal, well, here's a more complex or more fine-tuned, I would say, tool to help you determine whether your data is normal. So I'm indicating what the statistics are here, but unfortunately, we won't have the time to really explain what this means in detail. I really just want you to remember that these tests, they're a must-have in your hypothesis test toolbox because they allow you to verify one of the most common assumptions of hypothesis tests, and that's normality. Unfortunately, they cannot be done in Excel, so you will need more advanced software such as Minitab or R. Okay, because the test I will be presenting today, they're parametric tests, meaning that they all assume that the data at hand, it is normally distributed. There is a way to use hypothesis tests to analyze non-normal data. These are non-parametric tests. Unfortunately, they're generally less powerful than the parametric alternative. So if you know that you have normal data, you're much better off using the parametric ones. So the F-test is one of these parametric tests, assuming that, yes, the data is normally distributed, but also independence. So this means that the value of one observation, it doesn't influence the value of another observation. The F-test, it looks for a difference in variances. And the test statistic is the ratio of variances between the two groups. So it's really simple. This test, it's often used prior to other tests or inside other tests, such as ANOVA. In forensic toxicology, it is mentioned in ASB standard 56 on measurement uncertainty. So you can use it to see if the variance is the same for your different QC levels, because if it's not the same, you'll have to deal with uncertainty separately for the different QC levels instead of, just grouping them all into one big uncertainty. Okay, so how do you test for the mean? Well, you use a student t-test, for example. So it has similar assumptions to the F-test, and it looks for a difference of means. And to do so, it uses a sort of relative difference label T, so it's generally the difference in means divided by a standard deviation. We've seen that in the slides before, right? And the reason I haven't put a formula here is because you've got several different types of t-tests, and they each have a slightly different formula for t. So you have, for example, one sample, two samples, or paired t-tests. You can also assume equal or unequal variances. Okay, what if we want to compare more than two groups? Then we might want to use the analysis of variance, or ANOVA for short. So ANOVA, it assumes that the measurements are obtained independently and randomly. Plus, it is also a parametric test in the sense that it assumes the data for each factor level is normally distributed. So it looks for differences in data coming from more than two groups, and underlying it all is the F statistic. So there are a lot of variations on the ANOVA theme, a lot. Statistics textbooks, they usually have a full chapter or more dedicated to it, right? But just as a way of example, one way ANOVA, it looks at several repeated measurements for two groups or more. So if we do replicate measurements at different levels of a single factor. So as an example, if I do 3 replicate measurements of a caffeine peak with 3 different chromatographic columns, A, B, and C, then I could use ANOVA to tell whether there is a significant difference in the peak areas for the different columns. A two-way ANOVA looks at repeated measurements for 2 factors set at different levels. So for example, I take replicate measurements not only with the different column types, but also with different thermostatic temperatures, right? Is there a sensitivity difference across the different settings? You might also have heard about ANOVA lack of fit, which looks at a regression, so for example, a calibration curve, to examine if the variance due to the lack of fit is greater than the variance due to the pure error. So these are just some of the most common examples for a toxicology context, but as I've told you, ANOVA, it has very diverse application and settings. So to close this March, we have 2 tests for outliers. We have Dixon, or Q-test, which is popular mainly because it's so simple. It just uses the gap of the suspected outlier with the nearest value compared to the overall range of data points. Grubs is a bit more complex, but more powerful and preferred by ISO. It looks at the gap between the suspected point and the mean, and it's normalized to a standard deviation of the sample. And as a bonus, it's available in the 1 outlier and 2 outliers version. So here, I don't want to get into when these tests should be used, because this is an almost philosophical question, right? For the outliers test specifically, I mean, because some people might say that you should only remove an outlier when you have an underlying explanation for the deviation. So for example, say you misspiked a sample and you know about it. Others will say you can remove an outlier when one of these tests flags it as an outlier. But then, how do you know you haven't removed a legit data point? Because some data points are going to be coming from the ends of the distribution, right? From the tails of the distribution, right? So any distribution has extreme data that is perfectly legit and that you shouldn't reject. So anyways, suffice to say, there is a debate here, and you should use all of this at your own risk. Okay, so if we go back to our initial example of 2 blood ethanol quantification methods, how can we apply what we have learned today? We have 6 QC samples for each the historical method A and the recently validated method B. Well, the first thing we want to ask of our data is it normal? Does it follow a normal distribution? Because remember, most hypothesis tests, and certainly all the ones that I've listed here, they rely on this normality assumption. They are parametric tests. And So we need to ask this question for both the dataset of method A and the dataset of method B. So we'll apply a Kramer-von Mises test. Its null hypothesis is that there is no difference between the data measured and the normal distribution. So I apply this to dataset A, and I get a p-value of 0.92, and I apply it to dataset B, and I get a p-value of 0.8. So both of these, they're way above 0.05, so there's absolutely no significant difference from a normal distribution. Both data sets, they can be considered normal. That said, we're doing a test using two very small samples of only 6 data points. So there's a caveat to how strong this conclusion is, because the smaller a sample is, the more outrageous the difference needs to be for the test to pick it up. But anyways, normal distribution, it seems like a correct assumption here. Okay, so now we know that we can use all of the parametric tests since we have normal data, or anyways, data that is not significantly different from normal data. So we'll move on and ask the next question. Are the variances different? Well, for that, we'll use an F-test, since we have no reason to believe that the new method and since we have no reason to believe that the new method will have greater or smaller variance than the historical one, as we've said before, we'll use a two-tails test. So our null hypothesis is that variances are equal. We run the test and we obtain p equals 0.13, meaning there is a 13% chance of obtaining this data, or more extreme one, if the null hypothesis is true. Okay, 13%, it's not crazy low, so it's possible that the variances are indeed equal. But are the means different? Well, let's look at this with a t-test. We'll use a two samples test, right? Because we are comparing two distinct samples with one another. And it's two-tailed because we have no reason to believe that our recently validated method will yield smaller or larger results than method A. So we carry out the test and we get p equals 0.035, meaning there's a 3.5% chance of attaining this data, or a more extreme one, if the null hypothesis is true. Well, that's rather unlikely, isn't it? And it's certainly lower than our 5% threshold. So we'll say that the means for method A and method B, they are significantly different. And our final conclusion is that there is a statistically significant difference in the means of historically validated method A and recently validated method B. All right, so a few parting slides now. If you want to go down this rabbit hole a bit more and learn more about hypothesis tests, what they are, but what the criticism against hypothesis tests are, right? Because you might read that some people say we should really dump it all in the garbage. Nice of me to wait until, the 44th minute to tell you that. But anyways, what are the alternatives, the possible alternatives to hypothesis tests? Then I invite you to head over to my statistics series in the TF Bulletin. As I mentioned earlier, there are 8 published chapters so far, and chapters 4 and 5 are devoted to hypothesis tests and the debate surrounding hypothesis tests. If you're not a TF member and you don't have access to it, just shoot me an email and I will send you a link to a folder containing all of the issues. Otherwise, it's $25 per issue, which, it would be cheaper to become a TF member at this rate. I am still working on new chapters as family life allows, and I have several ideas lined up, such as statistics for validation procedures and trend monitoring, but I'm sure you will be covered just fine by Sue's upcoming presentation in this webinar series for trend monitoring at least. But if you have any other topic that you would like to cover, don't hesitate to email me. I'm happy to hear what the needs of the community are. And before I leave you, I wanted to highlight a couple of great references you might want to look into. And so statistics by Friedman, Pisani, and Purves is really an absolute gem for people with no, and I mean absolutely no training in statistics. One Amazon reviewer gave it a 1 star because I quote, "There are no formulas in there, just a square root here and there." And I think we can all agree this cuts it both ways, right? It might be exactly why you would give it 5 stars. So great examples, engaging writing style. It's all around really a lovely reference. The Lady Tasting Tea by Salzberg, it reads like a novel. So it's a book on the history of statistics, but you pick up a few concepts along the way. It places a lot of the stuff we've seen into context. All right, so thank you everyone for attending the session, and I hope you learned some things today. And I really want to thanks to Inaria for inviting me over. If you have any questions, comments, discussions, feel free to reach out by email or via social media. I'm easily found on most platforms. Might be a bit slow to answer due to my parental leave, but I will definitely answer any message. And right now, I will be happy to answer any questions that there might be.
Okay, so one of the questions is, in what circumstance would it make sense to conduct a two-tailed test before narrowing down to a one-tailed test?
Probably David can back me up here, but I'm not sure it's actually it's a good practice. It's actually not a good practice to do a 2 tails and then narrow it down to a 1 tail test. So you should really just pick your lane from the get-go and stick to it. And if you do one test after the other, you need to apply sort of a correction. If I'm correct, that is called a Bonifari. I don't remember the exact name, but there is a correction that you need to apply to account for the fact that you did more than one test basically on the same data set, and that it oriented your analyses.
Great. Thank you, Rishi. And the other one we had earlier was, how do you calculate the p-value without using Excel?
I'm assuming without using Excel and more complex software, because my go-to answer is, if you're not using Excel, use Minitab or use R. But it's even more complex software, and in the case of Minitab, it's also software that you need to pay for. In the case of R, it's free software, but the learning curve is a bit steep. So what I would say, if you basically no software, what you would need to do is to have tables for your statistics. So if you take the F test or the T test, you can find those tables online easily. And so these tables, what they look like is, you have your degrees of freedom in the different lines, and then here you have the significance level. And so basically what you would do is you would calculate for example, if you would do a t-test, you would calculate a t-value, and then you would go to the right degrees of freedom, and then you would go down the row until you reach your statistic, and then you would say, oh, okay, that's approximately a p-value of whatever the significance level is at the top. So that's a bit how you would do it, using some tables. These tables, they're found online. Make sure you use the right 1 tail or t-tail or 2 tails table. As someone said in the chat, there are tables also in textbooks that are available. So that's how you would do it. And mind you, this wouldn't give you like a precise p-value like 0.0135. It would give you just some it's approximately between 0.05 and 0.01, for example.
Okay. And our next question here is the effect of increasing degrees of freedom on the t-distribution rooted in the same concept of increasing sample size on the density curve described in session 2?
Yeah, exactly. So since degrees of freedom is the total number of the size of your sample minus 1 if you have one group, or minus 2 if you have 2 groups. So it's the two are linked, right? Then the sample size and the degrees of freedom, they're I'm going to say linked, but you know, more than that, they're equivalent. They're pretty much equivalent, -1 or -2, right? So yeah, it's rooted basically, yeah, in the same thing as we've seen in the previous webinar. And so what you're going to see also is that if you increase degrees of freedom, you're going to see a very large effect when you start increasing your number of samples. So for example, you know, jumping from 2 measurements to 10 measurements, you're going to gain a lot in terms of accuracy, precision of your conclusion. But jumping from 30 to 62, you know, you're not going to gain so much. And so this can also guide you in terms of how many measurements is appropriate for you and where you can get the most bang for your buck in terms of increasing the number of measurements.
Thank you. I think we have time for at least 1 or 2 more. So how might you justify a p-value that's 0.1 or even 0.2 to be less biased toward the null hypothesis?
Well, so the lower you go in the p-values, actually, the more bias it's going to be in favor of your null hypothesis. So if you're at 0.5, anything that has 5% chance or less of a chance of being from the null hypothesis, you go, okay, that's different. If you're at 0.01, it's anything that has a 1% chance or less of being from your null hypothesis data that you go, oh, okay, that's different. So the more you lower this value, you know, the more you're biased in favor of the null hypothesis, and the more of a difference it takes to trigger the significant difference. So actually, if you would like to reverse it and be less biased in favor of your null hypothesis, then you would need to increase the alpha value. You would need to increase it to 0.1 or to 0.2 or whatever. It's rare that we see it increase higher than 0.1, I'm going to say. But if you increase it, for example, to 0.1, then it's anything that has a 10% chance or less that you call significant, right?
Okay, and then let's see, what are one of the common or specific misuses of hypothesis testing in forensic toxicology? If you can do that in a minute.
Oof.
Or we can get to this one on the fireside chat.
Yeah, I think yeah, you know what? I think I would leave that to the fireside chat, and I could come up with like more specific example than just going off the top of my head, and then we could have something that's a bit, you know, a bit more complete answer.
So we'll save that for then. We're at the top of the hour, so I hope to see everyone for our session 4, use of controls and other control chart elements on Thursday, June 20th. So thanks everyone for coming.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.